Did you start recording already? Okay. I have the mic here. Okay. Good morning. I hope you guys all slept well after the drinks yesterday. Um, so today we're gonna start talking about the chiral Lagrangian and theta dependence of the theory of QCD below the scales of GeV or so. I guess before we start talking about that, I should ask if there are questions from last time that we should address before going on. There's also a question and answer session today in the afternoon, so the longer questions we can wait. But if there's quick questions that would help before going on, we could start with that. Okay, nobody has a very urgent question. So here's the rough plan for today. Try to see how much we can go cover. So we want to talk about the chiral Lagrangian, and the idea is to understand how in the real world QCD, this theta dependence that we have been tracking in toy examples show up. So it'll just be sort of there'll be some gentle introduction to the chiral Lagrangian that I want to go through, and talk about the theta dependence in the standard model. Um, the theta dependence in the standard model, by the way, will also teach us something something interesting about a theory that we're going to talk about eventually, which is the axion. As we'll see in a couple of lectures, the axion essentially is a field that makes theta dynamical, as we've said a couple of times. So this also tells us about the dependence of the standard model on the axion. In other words, the axion potential. So the computation of the axion potential can be carried out by treating the axion as a constant field. A constant field is just a parameter theta. So the theta dependence of the standard model that will compute will also just directly give us the potential for the axion. We also would want to, it would be interesting to study the theta dependence of the theory in the theta dependence of, let's say, pure Yang-Mills theories. So the difference between the standard model and a theory, a pure Yang-Mills theory, is the presence of light quarks. So as we'll see that the presence of light quarks in the standard model lets us write down the chiral Lagrangian and gives us a handle to calculate theta. We also believe, as we've been talking about in the context of these toy models, that even if we had no light quarks, the low energy theory of pure gluodynamics would also have theta dependence. And that theta dependence is also interesting, although we don't quite have the same tools as the chiral Lagrangian to talk about them. And in particular, for both of these cases, there's interesting things happening at theta equals pi that we will talk about. Okay. And finally, hopefully we'll still have time to then go and revisit the massless up quark limit. So in some sense, this will mark a transition for us from just talking about the strong CP problem and understanding the theta dependence of this theory to actually now talking about resolutions. In some sense, this would have been a very compelling and an elegant solution to the strong CP problem. So the punchline, the spoiler punchline is that at the end, lattice data shows that this is not actually realized in the real world, but it's actually quite subtle why this actually does not work out, and naive arguments why it does not work out are not correct, and it's also instructive to see how this would solve the strong CP problem if it did solve the strong CP problem. Okay, so that would be the rough plan for today. So let's begin with writing down the chiral Lagrangian. The starting point is to first write down the theory above a couple of GeV scale. So above a couple of GeV scale, we're still in perturbative QCD regime. So we can write down the Lagrangian for QCD that we've written down a couple of times now. Um, So at a couple of GeV scale, we can integrate out all the heavy quarks. We can integrate out the W bosons. We could add higher dimensional fermion operators here to for the weak interactions. But just focusing on the QCD Lagrangian part, we have the up, down, and strange quark, which we would treat as light quarks in our theory. And to the extent that they're light, this mass term, mass is a small parameter, and so this theory has an approximate symmetry, which is the chiral symmetry, which is called the chiral symmetry, which is independent rotations of the two chiral partners in up and up conjugate. And so these individual rotation in each for each of these particles would be a symmetry in the limit that in the limit that m was 0. When m is small, then this would be an approximate symmetry of our theory. Okay, this is a global. So this is the global chiral symmetry of the QCD Lagrangian. Okay, and the idea is that while we don't know what happens when QCD becomes strong and confines, we can track this global symmetry, and we can write down a low energy Lagrangian that is an appropriate that has appropriately this global symmetry in the limit of the quarks being massless. So so there's a beautiful story of trying to deduce what this low energy theory could be. Which I'll mention but not go through in detail here. The general idea is that of anomaly matching, which some of you might have seen already. And the idea is that we have global symmetries in our theory. Some of these global symmetries have anomalies. Anomalies are something which are topological properties of theories. And so it doesn't matter whether you're studying the theory at the weakly coupled phase or the strongly coupled phase, you can always track anomalies. And if you can look at the anomaly structure of this global symmetry in the QCD Lagrangian, that also tells you the anomaly structure of the theory in the low energy Lagrangian, and that can help you deduce what the low energy Lagrangian has to be without knowing in detail the dynamics of strongly coupled QCD. Okay. Is there a question? No. Okay. So the chiral Lagrangian then describes the physics of low energy physics of QCD. We can deduce using 't anomaly matching conditions that this chiral symmetry must be spontaneously broken, and this approximate symmetry. If it was a exact symmetry that was spontaneously broken, we would get Goldstone bosons. Since it's an approximate symmetry, we get pseudo-Nabu-Goldstone boson. So we get light fields, which are pion fields, which correspond to the spontaneous breaking of this global chiral symmetry by QCD effects. Okay, how many people have seen this before? Okay, good. If you haven't seen it before, I suggest looking at the chiral Lagrangian one time. It's an interesting system, not just because it gives us a handle on QCD where it's strongly coupled, but also the Carrel-Lagrangian was, I think, if my history is not incorrect, at the first place where we started really thinking about quantum field theory as an effective field theory and taking non-renormalizable quantum field theory seriously. So in some sense, realizing that the Carrel-Lagrangian is actually a very good description of nature, and there's predictive power in the Carrel-Lagrangian, was very important in understanding the modern version of quantum field theory as we understand, including non-renormalizable operators. And so the old style of saying that any non-renormalizable theory is sick and we should throw it away was all that was all brushed aside when we realized, in the context of the Carrel-Lagrangian, that actually effective field theories make perfect sense, even in the presence of higher dimension operators. Okay, so as an effective field theory, it's a very good toolkit to understand the rules of quantum field theory and how modern quantum field theories work, including non-renormalizable operators. Howard Georgia's book on weak interactions is a very good place to learn about the Carrel-Lagrangian. He also has a very nice description about anomaly matching. But there's other places you could, there's other places you could learn the Carrel-Lagrangian as well. Okay, so the Carrel-Lagrangian is parameterized by this 3x3 matrix field written as U, and so yeah, so let's write it down. So the symmetry breaking pattern of this global symmetry is that this global symmetry we started with is broken down to U1 baryon. So the vector symmetry or the baryon number symmetry of this Lagrangian is not broken. So how many generators are broken in this symmetry breaking pattern? Sorry. Now, how many symmetry breaking pattern? How many generators are broken in this symmetry breaking pattern? Right. So counting here, 18 generators on the left-hand side, but here there's 8 and 1, 9. So there's 9 generators that are unbroken and 9 generators that seem to be broken. So 9 broken generators, if you apply Goldstone's theorem, will tell us that we should have 9 Goldstone bosons. Okay, so what we can do is we can write down the Carrel-Lagrangian for these 9 Goldstone bosons, and what we can derive from the Carrel-Lagrangian are so-called sum rules. And one of the exercises that you would do is, hopefully do, is to look at a Carrel-Lagrangian with for the 9 Goldstone bosons and derive a sum rule so the 9 Goldstone bosons would be the pions, the kaons, the eta, and the eta prime. And you'll derive a sum rule that shows you that is in disagreement with data. So what you'd find is that the sum rules predict, in particular, it predict a mass of the eta prime much smaller than the observed value. Okay. So it seems like we had this global symmetry in the theory. Goldstone's theorem seems to predict 9 Goldstone bosons. We can actually we have predictive power in the Carrel-Lagrangian. And we can predict the masses, at least some rules for the masses of these Goldstone bosons. But it seems like we run into a problem with observations. We don't actually see 9 Goldstone bosons. I'm sure many of you have seen this story before. Maybe you can tell me what the resolution is. Very good. Yes, the U1 asymmetry was not a symmetry, as your previous exercise was supposed to show, that this symmetry is actually anomalous. And um, let, let's be a slightly more precise in our terminology. Uh, in the uh, in the modern way of saying things, when we say anomalies, the U1 asymmetry has anomalies with QCD, so that it actually has a what we call an ABJ anomaly. In other words, um, it's not just an anomaly between global symmetries, that's actually an ABJ anomaly, which means that when you write down, let's say, d mu, j mu 5, the divergence of the current associated with the U1 asymmetry, you get something which is like f g mu nu, g mu nu tilde. And these are dynamical fields. These are not these are actually gluons on the right hand side, which means that the symmetry actually is just broken. It's not anomalous. So there's a distinction people draw in modern terminology between anomalous symmetry, which could be anomalies just between global symmetries. What that means is, because this is a bit of a tangent, but worth going through. And an anomaly is just between global symmetries, which tells you that if you gauge some of those symmetries, you might break them, or you might not be able to gauge all of the symmetries altogether at all. So anomalies are then obstruction to gauging. ABJ anomalies, so this sort of mixed anomaly between a global symmetry and a gauge symmetry, quote unquote, is really just breaking of the symmetry. Okay. So in the modern QFT literature, you'll find this distinction that if you have an ABJ anomaly, you should just think about that symmetry as not being present at all. If you have just an anomaly between global symmetries, the symmetry is perfectly good, but you might not be able to gauge it. Or if you gauge some part of the symmetries, you would break the symmetry. Okay. Anyway, so going back to what we were talking about, the U1 asymmetry has an ABJ anomaly with QCD, and hence is broken. And so this was called the U1 problem. The problem being, where is the 9th Goldstone boson? And the fact that there was an anomaly, as well as this, the first appearance of instantons having effects in the path integral, convinced people that the U1 problem wasn't a problem anymore. So Satov showed that this U1 axial has an anomaly, and instantons exist for QCD, which can actually make which actually have physical effects. So they actually contribute to breaking of this U1 axial symmetry, and so this symmetry is explicitly broken even in the limit the mass goes to 0, and so we don't get a eta prime Goldstone boson. Okay. So historically, again, this was important because this was one of the first appearance of instantons in gauge theory. But again, I think the instanton calculus that shows that the UN symmetry is broken is not really reliable around the QCD scale. So at high energy scales, you can carry out an instanton calculus, and you get answers very analogous to the one we calculated for the particle on a circle. You get, if there's an instanton of winding number n, then you get a dependence on theta by e to the I n theta. But once you get to strongly coupled QCD, it's not really clear that that calculation is reliable. In particular, what we were calculating, if you remember, we were calculating contributions which were summing over instanton anti-instanton sprinkled randomly from from t initial to t final. And what we were doing was we were saying that the contribution of n instanton is just n times the contribution of one instanton. So we said The S classical for n instanton was n times S classical for one of them. And this is what is called a dilute instanton approximation, where each instanton is well separated enough that you can treat each instanton separately, and you can carry out the calculation with it. And the gauge theory calculation goes in the weakly coupled limit. The gauge theory calculation goes through exactly the same way. Once you get to strong coupling, the instanton density is no longer, the instantons are no longer sparse. There's not a big exponential suppression to their action. And so the dilute instanton gas approximation breaks down. And so at the end, the modern take is that it's not clear that it's actually instantons that are responsible for breaking the U1A symmetry. So it's true, U1A is anomalous, ABJ anomalous with QCD, and it's broken, so we should not expect the eta prime to be a massless goldstone or a light goldstone. Whether it's actually instantons in a calculable framework that contribute to the eta prime mass is not really clear. There's no reliable approximation scheme in which you could say instanton gives mass to the eta prime, which would have been the historical answer. The first time people said that U1 problem was resolved, that instantons give eta prime the mass, and that's why eta prime is heavy. The modern take is that that's not entirely clear. There's no reliable statement when it could be. But nonetheless, U1 axial is broken, and eta prime does get a mass from QCD effects. Questions? Okay. Yes, questions, sorry. Yeah, I mean, so the question is whether we can answer this question of what is contributing to the eta prime mass using lattice. I actually don't know what the status of the lattice calculation of the eta prime mass is. But yes, I mean, in principle, there's nothing on the lattice that stops you from answering the question. It might also be that in the lattice, you just sum over all configurations, over all possible winding numbers, and there's not a clean answer to say that this kind of configurations are the ones that contribute. You do the whole path integral in the lattice, and you find the pole or whatever, you find the eta prime mass, and you say that's the answer. But you can't necessarily qualitatively figure out, oh, there's a semi-analytical approximation scheme in which I could say it's like a dilute instanton gas in some approximation, right? So certainly you can find the whole spectrum of mesons on the lattice, but there might not be a nice weakly coupled or an analytical or qualitative answer to saying that kind of physics contributes. It's just the anomaly exists, and then there's nothing protecting the eta prime from getting a mass, and so field configurations just contribute to its mass, and there's no good approximation scheme. But I don't know what the status is of how reliable estimate, what is the sort of current state of the art for lattice predictions for the eta prime mass. If somebody knows or finds out, please do let me know. Okay, so that's the idea. Instead of 9 Goldstone bosons, what we're in the standard model, what we're supposed to describe are 8 Goldstone bosons. But there's a limit in which the eta prime also does become a Goldstone boson, which is the large N limit. So the effects of anomalies, the effect of the ABJ anomaly, so large N meaning large NC. So the QCD has NC equals 3, and I leave it up to you to decide whether NC equals 3 is a large N or not. But if you took QCD at large N, the effect of the anomaly is 1 over N, and so At n equals infinity, the anomaly goes away, and then again you recover all 9 Goldstone bosons. So it is instructive, even though in the real world it's not really a Goldstone boson. It's instructive to work in this large n limit to construct our Lagrangian for all 9 of the Goldstones, and keep a leading order, retain the leading order behavior in 1/n, just so that we have both eta prime and all the mesons all together in one place. Okay, this discussion, by the way, is parallels the discussion in this classic paper by Witten. Um, and this paper was written, I think, late 70s, and I invite you to read this paper. It's an amazing paper, and it sort of basically predicts all of what's going to happen in various limits of QCD 20, 30, 40 years down the line. So it's a really prescient paper, and it's a very readable paper as well. So I urge you all to read it. So we're going to follow roughly that logic to say we're going to construct the chiral Lagrangian for all 9 Goldstone bosons, including the eta prime, with 1/n, with 1/n suppressing its potential. Okay. Okay. So U is a unitary matrix. So U dagger U is just 1. So if you start making our Lagrangian with in U's, if we don't use any derivatives, there are no invariants under the global chiral symmetry that we can write down at all because of this fact. Any Lagrangian that you write down, which would be invariant under this global chiral symmetry using U, would just be a trivial operator U dagger. So the only non-trivial operators we would get involve derivatives of U. Okay, so the idea of the chiral Lagrangian is that we've parameterized our Lagrangian in terms of these Goldstone bosons. We should write down all possible general terms that are consistent with the global symmetry of QCD, at least up to the effects of the mass breaking the global symmetry, and we should write in all possible terms, and then hopefully there would be an expansion. In this case, it would turn out to be an expansion in the derivatives that will tell us, that will give us predictive power in the Lagrangian. Question, yes? Exactly, yeah. So in real QCD, you would argue that this is not really a perturbation. So then that's why we don't actually, phenomenologically, we don't see a light eta prime. But if n were large, you would also find the eta prime is large. And we'll see we'll write down the potential for it. And indeed, there's a perturbation in m, there's a perturbation in 1/n, which are both different perturbations which break the symmetry explicitly. In the limit of n going to infinity and the mass going to 0, the symmetries are, this is the global symmetry, so you should get 9 massless Goldstones in that limit. Good. So then we start building our Lagrangian. The first term that we can write, that is SU3 cross SU3 invariant, is a 2 derivative term, which looks like this, and the dimensions are usually parameterized by this quantity called f pi, which is the pion decay constant. And so the leading term in the Lagrangian that you could write down is actually just the 2 derivative term. And you can then go ahead and write down higher derivative terms in the Lagrangian, order d to the 4th, and so on. So the idea of the chiral Lagrangian is again that we build the most generally effective field theory with some cutoff in mind, and we can write down all operators consistent with our symmetries, which are this global chiral symmetries broken in a small amount by these explicit breaking patterns. Yes. So in Sorry, say again. Um, so there. If we think about the if you think about the 9 Goldstone boson, um, um, the 9 Goldstone boson U, there's another term that you can write down that turns out to be 1/n suppressed. So so if you just think about the kinetic term for the pions, that this is the unique term that you can write down. There's an extra term that you can write down that involves eta prime, but that turns out to be 1/n suppressed. So this is actually the leading term in 1/n and the chiral symmetry. Okay, this is the statement that f eta prime and f pi are the same to to leading order 1/n. So, but notice, by the way, if I expanded u in the pion fields, this is the kind of term that will, including other terms. This includes kinetic term for the pions, for example, but it also includes arbitrary number of interactions, arbitrary number of pion fields. So already this term is not a. It's the leading term, but it's not a free theory. It involves arbitrary scattering and amplitudes between different number of pions, because it's an e to the I pi field. Good. Right. So we could write down higher order terms, but what we want to next what we want to do actually next is to keep terms to second order and derivatives and include the effects of symmetry breaking and see how one would do that. So we want to figure out what is the leading term that that contributes to the symmetry breaking in the chiral Lagrangian. If we use this Lagrangian, then we'll see that the pion actually has a shift symmetry. Since u always comes with a derivative, the pion always comes with a derivative. If the pion momentum goes to 0, all amplitudes go to 0. So so we recover the well-known fact that the Goldstone bosons are derivatively coupled, and the pion would have a shift symmetry and would be exactly massless. So to include symmetry breaking effects and to recover the pion masses, we have to do something to say, well, we had this explicit breaking in the QCD Lagrangian as well, and we want to include its effect in the chiral Lagrangian as well. And the way we include its effect is to notice that we can, in the QCD Lagrangian, we can elevate M to be a spurion. So we can give fake transformation properties to M under the chiral symmetry. We can say M goes to M goes to let's say M goes to something like this. Now, of course, M is a fixed parameter, so M doesn't transform under any of your symmetry transformations. But if we assume that M goes to this under, say, a global chiral symmetry transformation, then the QCD Lagrangian would actually be invariant under these transformations, right? So then actually we would actually have, including spurious transformations of M, we would actually have an exact symmetry in the QCD Lagrangian. And so the rule for constructing the chiral Lagrangian would then be to respect that exact symmetry. So in other words, we can now construct invariance using M and perturbation theory in M. So if M is small, then we could use M dagger M. We could use all these quantities, which now have the spurious transformations, but the rule is to form invariance in the chiral Lagrangian using these quantities. Okay? Is that clear to everyone? So the leading order term that you can write down, the leading order term in the perturbation theory in M is this quantity. So at leading order, you can see that U transforms as Uh, Under SU3 left cross SU3 right transformations, our matrix U transforms in this particular way. If we ascribe a spurious transformation to M, the M would transform like this, and so this quantity trace mu would actually transform, would actually be invariant under SU3 left cross SU3 right. So this would be the leading order term in the Chiral-Lagrangian that would appear as a breaking effect. Now we go back to the actual physical situation, saying, well, M doesn't transform, so this is not invariant. This is actually an explicit breaking effect in the Chiral-Lagrangian. It breaks the and indeed you'd find that this, for example, gives things. If you expand U out, this would give you terms like mass of the pion. So when you actually carry out this exercise to calculate some rules for masses of goldstones, that would be the idea, to say that I assume that global symmetry and I write down this leading order term. My original Lagrangian had 3 parameters: mass of up, mass of down, mass of strange. That was the mass term. That was the mass matrix. So there was only 3 parameters that were unknown, and then I would have this would maybe come with some undetermined parameter as well. Let's call it sigma. So I would have those 3 undetermined parameters and 1 coefficient of this Lagrangian term, and that would fix the entire spectrum of mesons. So this would be a predictive theory where if I go and measure all the 9 meson masses, and I compare it with the 3 unknown quark masses and this unknown coefficient of the Lagrangian, I should be able to get some rules out of that and get predictive power and check whether this is a reasonable approximation or not. And you would find that you can rule that theory out with 9 Goldstone bosons in the real world, because mass of the eta prime would not fit in the sum rules. Okay? Is the logic clear to everyone, or other questions? Okay, so this is the Chiral-Lagrangian in 2 derivative order. We have to add one more thing, because we're keeping track of the eta prime as well. There's also an explicit breaking term that we have to write down that parameterizes the effect of the anomaly, and we won't have time to go into the detailed arguments of why that takes this particular form, but you can look at this paper that argues that the leading order effect would have to be something like the rough idea is that the anomaly is in the eta prime part of the symmetry. So it's in the part of the symmetry that is not the special unitary part, but the part that is the U1. So it can only be proportional to det of U, and large uncounting arguments can be used to say that it actually depends on log of det of U. It doesn't depend on det of U, but actually log of det of U. Okay, but the idea here is, again, this is just like we argued on symmetry reasons. What the leading breaking term for the Chiral-Lagrangian as a consequence of M would be, you can also argue the leading breaking term in 1 over n because of anomaly would be this. So this together gives us the leading order Chiral-Lagrangian that we can write down at one place. Okay, um, and so this is a Lagrangian that describes the spectrum and the interactions of the nine Goldstone bosons. And so this has a few undetermined parameters. This mass matrix M that we don't have direct information about, and these coefficients. But you can see that you can now predict any meson process: 2 to 2 scattering, masses, 2 to 4 scattering. All of those are at leading order are predicted by this Lagrangian. So it's a very highly predictive Lagrangian, and so that is its power. But an additional thing that we actually care about is the dependence, the theta dependence. And so the next thing I want to do is to figure out what is the how does the theta dependence of the QCD Lagrangian show up in this chiral Lagrangian. We haven't really talked about that so far. Okay. So the crucial point is that by using this anomalous symmetry, we can perform a rotation of the quarks, a chiral rotation of the quarks that moves the theta angle from the topological term into the quark mass matrix. So if in particular, if you do a chiral U1 rotation, we find that the theta angle shifts by an angle alpha, that which is related to the rotation we did for the on the chiral rotation we did on the quarks. This is again a consequence of the chiral anomaly, and this is again the thing that one of your exercises is supposed to guide you through of how this chiral rotation gives you a shift. Yes. Yes. So the yeah, it'll show up in just a second. I've sort of so far. Let's say I've ignored theta, and so let's go back and fix that and see whether theta would show up. And indeed, this is exactly what we're doing now. Yes. Sorry, the here you mean? Um, it should be a so log that u is going to be like something like eta prime squared. What was it? E to the I eta prime. So log that would be I minus. Yeah, so there should be a minus sign overall here, just for minus m squared, eta prime squared kind of thing. So just for positive mass for the eta prime. So the crucial thing is that because we have light fermions, we can actually transfer the theta dependence in the QCD Lagrangian all into the mass matrix. So we can do a chiral rotation by an angle theta in that Lagrangian up there, and what it does is in particular, it takes determinant of m, and it phases determinant of m by e to the I theta. So if the quarks were massless, as we argued in our exercise, we could completely get rid of the theta angle by doing this chiral rotation. It would not show up anywhere else. Because the quarks are not massless, when we do the chiral rotation, the symmetry is not only anomalous, but also explicitly broken by the mass term, so this shows up in the mass term. But then this tells us how to account for theta in the low energy Lagrangian. We can, in the QCD, we could first do this chiral rotation and get rid of theta altogether from the GG tilde term and put it all in the mass matrix. We know how the mass matrix appears in the chiral Lagrangian, so all the theta information would be encoded now in the mass matrix in the chiral Lagrangian. Okay, so the presence of chiral symmetry, which is anomalous, gives us a handle to understand how theta would show up in this Lagrangian. In particular, what we can write m here as some diagonal matrix. Let's call it D. The diagonal matrix is m up, m down, m strange on the diagonals. Okay, at least proper. So, again, the logic is that we had the QC Lagrange. It had a theta term and a mass term. We do a chiral rotation. We get rid of the theta term, and put it all in the mass term. That QC Lagrangian we match onto the chiral Lagrangian, and the theta just goes inside M for the right wherever M appears. Theta would appear along with that. Any questions about that? So in this parameterization of the mass matrix, I can write so I would put M to be this, but then I can do a rotation U goes to e to the I theta over 3. I'm not being very careful about minus signs. They don't really matter. Let's say this was the parameterization of the mass matrix. I can do U going to e to the I theta over 3U, which would convert this term just to the diagonal matrix times U and put a theta here. Okay, so I've erased the equation, so maybe there's a couple of steps going on at the same time. I had an equation which was just a general equation of the chiral Lagrangian, where mass m contained all the theta information. I said I can write m as e to the I theta over 3 times d, and also do this redefinition of u at the same time. So all the theta dependence then shows up here. And now D is a real positive diagonal matrix. U parameterizes the pions, and all the theta dependence just shows up in the Lagrangian. So what this has helped us do is to figure out exactly where theta shows up in this chiral Lagrangian. The logic is just that whenever you have light fermions, you can always just, the theta angle interacts with the light fermions, the phase of the light fermions, and so you can just use that to calculate the low energy dynamics of this theory. So the next thing what we want to do is to look at this chiral Lagrangian and try to figure out the vacuum structure of this Lagrangian. Again, what we did in the quantum mechanics on a circle was to figure out the energies of the ground state and their theta dependence. We would like to do the same thing for this chiral Lagrangian. What that would involve is to minimize the potential for this Lagrangian. So the potential is given by these terms, sigma trace du and log det u, and we would minimize this term, and so that will give us what the vacuum expectation value of these fields are, and what the corresponding vacuum energy is. Okay. So first of all, this, if you look at the potential, the mass terms are diagonal in the matrix. So the vev for u will take the form because the potential itself is diagonal in u, the vev itself would be diagonal, and so if we actually just do dv phi equals 0 to calculate the minima of the potential, we end up with the following equations. Okay, so just to make contact with Witten's notation, let me just write the diagonal matrix in this form. And so what you get is probably I'm missing a factor of 2 here. Everything was scaled by f pi squared over 2. The quantitative aspects are not particularly important. What we're trying to understand how theta shows up in the low energy theory qualitatively at the moment, and these are the equations that we're trying to solve for the 3 phi i's. that tell us what the minimum of this potential would be. Okay. So in general, we could go ahead and try and solve this. This is a rather complicated equation. Doesn't really have analytical solutions in general, but we can solve it in certain limits. And we're going to do a couple of limits. One is sort of a semi-realistic limit where we treat A over n as much larger than the mass term. So the limit where the eta prime is the largest. So you could call it sort of the realistic limit, where we take this hierarchy where we would find when you do the sum rule calculation, you would find that these ratios are mu u squared, mu d squared. This is proportional to the mass terms in the quark of the quark coming from the quark Yukawas. And so indeed in the real world, in the so-called two-flavor approximation is we take this strange quark mass to be much larger than the up and down quark mass. And also the eta prime mass that is coming from this anomaly term is much larger than either of them. So this would give us at least a qualitatively a realistic an idea of what the realistic in the realistic QCD what the dependence on theta would be in the vacuum energy. Okay. So in this two-flavor approximation, we can actually solve this system analytically, which is why it's useful. When A over n is very large, that essentially fixes sum over phi I to be theta. And so that constraint in that limit, then what you find is sum over phi I equals theta. And the fact that it's a two-flavor approximation also sets the phi s to be 0. So we actually get phi u plus phi d equals theta. And mu squared sine phi u equals mu d squared sine phi. If you were calculating the axion potential in real world QCD, you do exactly very similar looking steps. And the solution that you find in this case is so sine phi u is this, sine phi d is this d replaced by u here. So you write u slash d, d slash u. So you can actually solve for the values of phi u and phi d in this thing, and then plug it back into the potential, and you'd find the vacuum energy of QCD. And there's a couple of steps of algebra to replace mu and md with the pion mass. Again, once you do this exercise of doing the sum rules in the Carrel-Lagrangian, you would see the relation between the pion mass and mu and md. But you can write it like so. Where z is just mu over md. Okay, so in the real world chiral Lagrange, in the real world QCD, this is the dependence of the vacuum energy on the angle theta, or this would be then when we make this into a dynamical field called the axion, this would be the axion potential in the real world. Okay, and the qualitatively the way we got this theta dependence was to say, well, we know that they're light quarks, so we can put the put the theta dependence in the quark masses, track it through the QCD phase transition into the chiral Lagrangian. So at leading order, we can actually calculate the theta dependence in the chiral Lagrangian itself without knowing details of these are all quantities that are measured or constrained by low energy data. We didn't actually need to know anything about strong interactions to get to this dependence on theta. Okay, if we wanted to do the same thing for pure Yang-Mills, things without light quarks, as we'll see, there's not that we don't have as much quantitative information in that case to actually say something robust quantitatively for all n. Okay, any questions about this so far? Yes. Where did we lose the large n limit? In some sense, when we said this, the whole n was only appearing as the coefficient of this anomaly. When we said this is true, we could be still in the large n limit. In the real world, you could argue whether that's true or not, but it could still be in the large n limit, and just in a limit where the masses of the quarks are much smaller than these coefficients, right? So even in the large n limit, if these if the mass parameters are much smaller than whatever the eta prime mass parameter is, then you would get this, and then you can compute 1 over n corrections to this, right? So if you just wanted to solve it in generality, you would just solve that equation that has explicit n in it, and you just solve solutions for it, and you can do that in 1 over n perturbation theory at large n. So you would get 1 over n corrections to this equation here. In the real world, it's not totally clear that. That's why this realistic is in quotation marks, because what we've been doing is we said we kept only the leading order 1 over n term for the eta prime Lagrangian. That may or may not be the right approximation, and so this is sort of at least qualitative to that extent. Question, yes? So in this discussion, A is just a free parameter. So good. So there's this whole philosophy known as naive dimensional analysis, where you're writing something like the chiral Lagrangian down, which is an EFT. That's a result of strongly coupled dynamics. Then the naive dimensional analysis, with emphasis on naive, is that you keep track of all the symmetries and then write down everything at some prescribed order, which would just be generated at order 1, where 1 means something. The rough rule is that you shouldn't write something that at loop order gets generated much bigger than what it already is. So everything is sort of generated fully. And the argument for that is it's strongly coupled, so whatever can get generated will get generated. So these are order 1. With large n, there's actually a nice large n counting of what parameters are large n. And so there's a nice counting for, nice counting for chiral Lagrangians with large n and derivative expansion, and you can then do a very precise power counting in those parameters. Good. Super slow. Yeah, so let's notice one interesting feature. Let's try to plot this function. So in the real world, mu over md is about 0.5. So so v of theta just looks like some sinusoidal function. It's not really a simple sinusoidal function, so it's not really sine or cosine, but it's some periodic function of theta. But let's see what happens in this hypothetical limit if we take, let's say, z equals 1. So in this limit, which is not the real world, where mu equals md, you see that this becomes, I should use a color that's visibly different maybe. So you want to take the limit z equals 1. Don't know if that's better. This actually becomes absolute value of cos theta at z equals 1. Have I got that right? Yeah. So the potential at z equals 1 has this interesting feature where it's actually like an absolute value potential. So if I plotted that, what I would actually get is, this is no good. Maybe red is different. I would get cusps at theta equals pi in the vacuum energy. Okay, just plotting absolute value of cos theta in this potential. So if you remember back in the maybe in the first lecture, we were talking about the particle in a circle. We were pointing out that the vacuum energy has this interesting structure where actually there's different branches of the vacuum that come and meet at pi, and that at theta equals pi there was a cuspy structure. That is reproduced here at this value of z equals 1 in the QC Lagrangian. And indeed, we'll see that this cusp has an interesting interpretation, which is similar to the interpretation of these branch crossings that we were talking about in particle in a circle. Okay? And this is also true, by the way, for the axion. The axion potential, if mu was equal to md, the axion potential actually would have a cusp at axion equals pi. Any questions so far about? Yeah, let me just say it. Let me say this rather qualitatively. Well, so here this particular cusp seems to happen only for z equals 1. We can actually do the three flavor analysis. So not take that. So don't throw away the strange quark. And in the three flavor analysis, what you find is that that you have these cusps if a certain condition is satisfied, which is if so let's see if this is true. Just trying to get the sign of the inequality correct. So if this would be true, then this whole this phenomena that we're seeing for the two flavor case is actually persists, where we actually see a cusp at theta equals pi. Okay, this is again not true in the real world. You can mu minus md is the same order as mu or md, and so this is not really true. So we don't actually have a cusp in theta equals pi. But this, if that were true, then this would be, there would be a cusp, and this is called Dashen's. What is it called? Dashen's phenomena. Dashen's phenomenon. Dashen something. Okay, so I just wanted to qualitatively understand what's going on in that particular. Uh, what is the quality in the standard model? There's no cusp. The dependence on theta is smooth, but actually, if you have theta equals pi, then actually, if you had these parameters mu md greater than ms times mu minus md, then you actually would get cusps. And so I wanted to show what the qualitative physics of that cusp is. Okay, the cusp at theta equals pi is interesting. Yeah, indeed. Exactly, good question. So at z equals 1, it seems like it's a consequence of mu equals md. So maybe it's the restoration of some flavor symmetry that seems like the reason. But actually, it's not to do with the restoration of flavor symmetry. Here, it's just generic in the whole parameter space like this. So you just get the cusp. And this idea is that so the idea is that that the solution. Sorry, question. Yes, of course. Yeah. So there's a. I mean, there's the. So it's minus cosine of theta, and this could be 1. So it's a. Is that okay? I mean, it's yeah. You could add the one. The 1 is just a constant, but the cusp is at theta equals pi, which is at the maximum. Theta equals pi. Um, so the rough idea of what the cusp is, the reason the cusp exists is, imagine that if you had when we're minimizing the potential, you could have either a unique solution. This is going to be a little bit of a cartoon, but hopefully you'll get the idea across. Or you could have multiple solutions. Um, so a unique solution just means you minimize the potential. You'll find that the potential looks like this. If you deform the potential smoothly, the potential will deform smoothly, and you would have as a function of theta, the vacuum energy would just deform smoothly as you change theta. If you have multiple solutions, for example, you have a local minimum for your equations of motion, and you have a global minimum for some value of theta. As you scan over theta, um, it's too big. What you could happen is that the relative position of these solutions would change. And eventually, for some other value of theta, you find that this is the true minimum. Okay? So whenever the equation that we wrote down, I guess it's erased now, this equation mu I squared sine square theta equals a over n, sorry, phi I equals a over n phi I minus. So this was our equation of motion. Because this is a function of sine theta, this could have multiple solutions. And indeed, what you can show is that if this is true, there are multiple solutions to that equation. And as a function of theta, you see that the vacuum energy could go to the lowest lying, the vacuum energy, the lowest energy of the system could go from this branch to this branch, and it would actually have to cross at some point. So what's happening again in these cases is exactly that whenever there's a cusp, the cusp is that the vacuum energy here is on one branch, and then here at some value, which turns out to be theta equals pi for an interesting reason, the other branch is now the vacuum energy, and so the vacuum energy tracks the dependence of that state as a function of theta. Okay, so that this presence of this cusp in this notion is an indication of kind of like a first order phase transition, where the vacuum energy is the E of theta. So let's call this 1 and 2. The vacuum energy as a function of theta is E of 2 theta for this half of the evolution, and it's E of 1 theta for this half of the evolution, and at some point they cross, and the crossing point is this cuspy point. E1 of theta and E2 of theta themselves are smooth functions of theta, but the vacuum energy itself is not a smooth function of theta. Whenever there is this first order phase transition, they cross with a cusp. Okay. So the presence of this cusp is not present in the standard model. In the standard model, there's a unique solution for the parameters we have, but it's a generic feature whenever you have multiple solutions for equations of motion. Okay. Question? Yes. Yes, indeed. So you see, these are sines and cosines. So depending on the parameters, there might not be more than one solution. So we might be in this situation where there's always just a unique vacuum, and as a function of theta, it just smoothly changes, and there's never this condition. So the condition for this cuspiness is exactly when you have these multiple solutions that switch, and the multiple solution that switch depends on parameters of your potential. And so for this range of parameters, you get multiple solutions for your equation of motion. You get this minimum and this minimum, one of which is the global minimum. Yes, and the crossover happens at theta equals pi. Uh, um, the crossover happens at theta equals pi for it happens at theta equals pi, and let me now evaluate if I have time to go through the part why that is cool. Yeah, essentially, the crossover happens at theta equals pi is because C. Okay, let's do this then. Yeah, so the behavior at theta equals pi is interesting, and so let's study it slightly more. Okay, so to study theta equals pi and the branch crossing, it would be interesting to actually study the theory in large N, but without any quark flavors. Okay, so we're going to now think about theta dependence. So the same cuspiness that we're seeing here at theta equals pi actually would show up in pure Yang mills. That is to say, a theory without any light quarks. So we did all this analysis. We had some control over the dependence of theta in the low energy theory because there were these light quarks. So we can just show, you can work through this analysis slowly, and you can just plot E of theta as a function of E as a function of theta for those parameters, and you'll just see this structure. So there's nothing mysterious going on. But now when we're talking about Yang-Mills theory, we don't really have the same kinds of analytical handles, and so the question is, can we understand the theta dependence of this theory? And again, we'll see the same theta equals pi behavior emerge interestingly. So there's a very nice Largen argument in Witten's paper, which again sort of almost qualitatively guessed the answer for what the theta dependence is going to be, and indeed turns out to be the right answer. And his argument is that on general grounds, one can show that the energy as a function of n squared and theta should have an n squared should have a dependence which looks something like this. Okay, so the energy, just because at n squared degrees of freedom, should scale with n squared. And the way the theta appears in the Lagrangian is through a 1 over n effect. Very similar to the fact that we argued that the anomaly in the Lagrangian was a 1 over n effect. Okay, so Witten argues using large n that this should be the form so this is some function. That will be the same function. This should be the form of the energy as a function of theta angle. But then this seems to be this seems to be in contradiction with the fact that this physics is supposed to be periodic in theta. So if you take theta going to theta plus 2 pi, a generic function of theta over n would just go to this, and there's no reason why this would be periodic again. And so Witten argues for this branched structure where the energy of theta has a structure which looks something like in other words, it's the same kind of structure that we saw in particle on a circle, where there's many branches of the solution. Here we were arguing for 2 branches of the solution in Dashen's phenomenon. At large n in pure Yang-Mills, we say there's many branches. There are n, capital N branches of the solutions. So k is 1 to n. And depending on the value of theta, one of those branches is one of the branches is minimized. Let me just double check, sorry. I'm just double checking a factor. What is this? So in the large n limit, each of these branches does not have 2 pi periodicity in theta, exactly as we saw in the case of our quantum mechanics of a particle in a circle. A given branch did not have this periodicity in theta, but the minimum or the spectrum of the theory at any given point is periodic in 2 pi in theta, and that's a consequence of this different branch crossings, exactly like it was the case for particle in a circle. So, question, yes. Right. So yeah. So this is that's what I was trying to. Yeah. So what I want to say here is, so this function is a function which is periodic with 2 pi n. So I want to say this is something like cosine n theta. And oh. So let's say f of theta was f was cosine. So then f of theta over n would be cosine theta over n. Yeah. So maybe I don't have this n squared out front. So this is as said that I extracted this n squared. So I could put an n squared that it was this thing. So let's take an example of something like this, where this function is not now of periodicity n to n pi, not 2 pi, right? So if this was the answer, then you would say the quadratic term would be theta squared over n squared times n squared. So it will just be theta squared, right? So this is the in the large n limit, and when n goes to infinity, then this is the theta dependence of the vacuum energy. Okay. If you wish, I could say something like n squared min of cos this over n. Okay, just to make that explicit. Does that answer your question? Sorry, this is not super clear. It's just the idea is that in the large n limit, the number of vacua goes to infinity, and so the function doesn't even have to be periodic anymore. But it's at finite but large n, it's periodic with a periodicity 2 pi n. The crucial feature that I want to point out here is, again, this is something we're doing in Yang-Mills, where we have no analytical control at all about we have no analytical control about any dynamics, and so we have no right to expect that we can get theta dependence of the theory. The large n arguments themselves tell us something interesting about the theory, which is that there should be branch crossing at theta equals pi. Similar to Dashen's phenomenon that we saw explicitly in the case of a certain parameter range in the chiral Lagrangian. Okay, so without actually knowing anything about strong dynamics, we can actually figure out that we can actually argue, at least in the large n limit, that there's some branch structure to the vacuum energy as a function of theta. And theta equals pi, again, the branches cross at theta equals pi. As you can see in this particular parameterization, which branch k contributes to the minimum jumps exactly at theta equals pi in that. Yeah, so I think what I'm going to do is to move massless up quark to next time, because I want to tell you an interesting connection. An interesting connection to very modern developments, and one of the poster childs for why generalized symmetries are useful. So this conclusion that we drew from thinking about the branch structure and an analogy with Dashen's phenomenon, you can also deduce using higher form symmetries. Okay, so this is going to be telegraphic a little bit, but I think it's worth just mentioning it. You can go and look at the papers, and I'll try to give you at least a cartoon picture of what the mathematical words mean. So there's a couple of papers by Seiberg and collaborators. Which try to elucidate the properties of Yang-Mills theory at theta equals pi, and indeed what they want to try and show is that theta equals pi, there are two degenerate solutions, and CP is spontaneously broken. They phrase it as time reversal, but in any theory with CPT, which is any theory with Lorentz symmetry, CP is the same as equivalent to time reversal, and so we can deduce again using using these arguments that I'm going to give you in a second, that at theta equals pi, CP is actually spontaneously broken in Yang-Mills theories. Again, they have a stronger argument in large N, but they argue that they probably the situation persists even for not necessarily large N theories. Okay. So the CP symmetry is indeed the reason why all of these crossings happen at theta equals pi. We said the crossing is associated with two vacua becoming degenerate. If they're two vacua degenerate near theory, there's probably a symmetry reason for why two vacua have the same energy. That symmetry reason is CP. Okay, so at theta equals pi, we have two CP conserving two vacua that are exchanged to each other by CP, and you have spontaneous CP violation in any given vacuum. So so let me say the words that. So at theta equals 0, there's a trivial gapped vacuum. There's a unique vacuum at theta equals 0. There's nothing that's like sitting at the bottom of one of these wells, and that's there's nothing more interesting than that going on. At theta equals pi, there is let me say the words and explain what they mean. Mixed a 't Hooft anomaly between time reversal or CP and the Zn one form symmetry of Yang-Mills. So in at theta equals pi, we said CP is a symmetry at theta equals 0 and at theta equals pi. How do we see theta goes to minus theta under CP? So at theta equals 0, obviously this is the symmetry of the theory. At theta equals pi, pi goes to minus pi, and then the symmetry and the theory is periodic in theta, so you can do a theta going to minus theta plus a 2 pi shift and go back to the original theory. And so at theta equals pi, the CP is also a symmetry, but there's an interesting theta going to theta plus 2 pi shift that's associated with showing that theta equals pi is a CP conserving symmetry. Okay, and so in this language we say that there's a branch crossing involved in that statement, and so the CP symmetry at theta equals pi is a little more interesting, and that's the notion of the CP symmetry. 2 points, theta equals 0 and pi. CP is a symmetry, and SUN Yang-Mills theories have a one-form symmetry. In this case, it's a discrete symmetry. It's a Zn symmetry, and it's a Zn one-form symmetry. So we've seen this one-form symmetry before. We've seen it in the context of when we talked about. We've seen a one-form symmetry before. When we talked about 1 plus 1 Maxwell theory, we said. So recall in 1 plus 1 Maxwell, in fact, even for 3 plus 1 Maxwell, the Wilson line or this operator. A on some spatial circle goes to the same operator plus a constant. In our quantum mechanics, this mapped onto a shift symmetry for our variable q Or in terms thinking about an actual Wilson loop, which was e to the I a, this was a phasing of that Wilson loop. Okay, so in this 1+1 Maxwell theory, if we thought if V of Q was 0, if you had no potential for the um, for our quantum mechanical variable, then there was a continuous shift symmetry, which was a global symmetry for quantum mechanics, the quantum mechanical variable. That global symmetry in the quantum mechanical variable descended from what we call the higher form symmetry in Maxwell theory. That higher form symmetry in this case was a U1, because this is a shift by any real number that you could do from 0 to 2 pi. A 2 pi shift was the gauge invariance of this quantum mechanical variable, so that we always had. But there was also a global symmetry in this case, which was this continuous shift of this variable. And in this case, it was a U1 one-form symmetry of the Maxwell theory that translated into this U1 symmetry of this Q, an ordinary U1 symmetry of the Q. Okay, so is this mapping, well, is this mapping confusing? Is there a question about this? Okay. Maybe it's worth mentioning here as an application, as a FINO application, that we'll talk about extra dimensional axions. As I was telling you, extra dimensional axions are very similar to this Q of T, where we have, let's say, a 5-dimensional theory, and this kind of loop operator in 5 dimension gives us a axion field in 4 dimensions. And so again, when we have an axion field, we would see that one of its crucial properties is that it's a Goldstone and it has a shift symmetry, at least an approximate shift symmetry. That approximate shift symmetry, again, descends from a one-form symmetry of the 5-dimensional theory. Okay, so we'll talk about it maybe, hopefully. So axion continuous shift symmetry, something which we are really which is of great phenomenological importance. That is the reason axions are light and can be detected in our low energy experiments. In extra dimensional axion model, descends from this, exactly this, in this way, descends from one form symmetries in higher dimensions. Okay, so 1+1 Maxwell has this one form symmetry, which is actually a U1 symmetry. It turns out that the so let's say some more about the U1 Maxwell before going on to the non-abelian case. What is the this is a global symmetry, so we could decide to break this global symmetry. We could have this global symmetry or not. And by the way, I should say, this U1 global symmetry is even present for, I think Anne was asking this question, that even for 4-dimensional Maxwell theory, we have a one-form global symmetry. So 3+1 Maxwell has a one-form. So Maxwell meaning only photons, no charged particles, has a one-form U1 global symmetry. These are, again, symmetries of, instead of local operators, these are symmetries of extended operators like Wilson lines and Wilson loops. So they act naturally on Wilson lines and Wilson loops. The explicit breaking of these kind of global symmetries takes the form of existence of charged particles. So in particular, QED, so theory with photons and electrons, the U1 symmetry is completely broken. Assuming electron has the fundamental unit of electric charge, which this is the standard assumption we make. Okay, The idea of breaking of these one-form symmetries is that if you think of this Wilson loops, so you have a Wilson loop. If there's no charged particles, this Wilson loop cannot be broken. You can't end it anywhere. The Wilson lines have to end on electric charged particles. If you have charged particles, you could end that Wilson line on that charged particle, and so that endability of the Wilson line is a sign of breaking of this global symmetry. So again, this notion of thinking about symmetries in this form is the cornerstone of thinking about higher form symmetries and casting symmetries in a way that generalizes not just to not just to symmetries acting on local operators, but extended operators as well. So the endability of Wilson lines tell you the breaking of the symmetry. In QED, if you have electrons, all Wilson lines can end, and so the U1 symmetry is completely broken. Imagine that you had some theory of Maxwell, but only charge n particles. So there's a fundamental quantum of charge for any U1, but your theory does not contain the fundamental quantum of charge. You only have charge n particles. So a Wilson line which has a unit Wilson line cannot end on this charge particles. N Wilson lines can end on this charge particles, but a single Wilson line is not endable. Is the logic of endability of Wilson lines okay with everyone? So in this case, what we say is the U1 symmetry is broken down to a Zn one-form symmetry. So these are two examples. So we had a Maxwell theory without charged particles. No Wilson lines were endable. And so we had a one-form global symmetry in that case. If you add charge 1 particles, that symmetry is completely broken. All Wilson lines can end. If you add charge n particles, only n Wilson lines can end. So your Wilson lines can have can be valued in Zn. But then once they're n Wilson lines, they can just end. Okay? Any questions about this? We should say the point of this is to give you an introduction from a phenomenological perspective of these developments, which I think are interesting developments in formal quantum field theory. So we don't necessarily need to go through this to understand the strong CPU problem, but this is a connector to all these developments in generalized symmetries. So if you see it in this context, hopefully you'll see the motivation for studying it in more generality as well. Okay, so and again, there could be entire summer schools. There are entire summer schools devoted to just understanding generalized symmetry. So this is supposed to just be a very quick, broad brush overview rather than a detailed introduction. So now let's go to SUN Yang-Mills theory. And in complete analogy with the U1 case, we would want to understand what kind of Wilson lines are endable and what kind of Wilson lines are not endable. So if we had no charged particles, if that were possible in the Yang-Mills theory, we would also have a U1 one-form symmetry. But a Yang-Mills theory always comes with charged particles. The gluons are charged under the gauge theory themselves. So there's always Wilson lines that can end on gluons, and so there's always only this condition that we have. So we have what is called I guess what do we call it? Is it called anality in anality or triality, right? So in SUN theory, there's something called anality, which is to say that if you don't have fundamentals in your theory, the certain flux tubes can't break. Right? In QCD, we have flux tubes, and if you take QQ bar very far apart, because we have fundamentals, every flux tube can break. But if you took a theory which did not have fundamentals, then the flux tube, not all flux tubes can break, and particularly Wilson lines in the fundamental representation would not be endable. So in complete analogy with this case, a Maxwell theory with charge n particles, there's a one-form symmetry for there's a one-form symmetry for Yang-Mills. Okay, so hopefully I've sort of motivated how one-form symmetries show up by studying our quantum mechanical example and an analogy with U1. The final bit of physics that we need to is to understand why do we say that there's a mixed anomaly between between time reversal invariance or between CP and Zn, especially at theta equals pi, but not at theta equals 0. And this is again something which we have seen, which is so I'm going to just, this is going to be extremely schematic, but this is going to show you at least some physical picture of where the anomaly comes from. What we said was that in the presence of theta for the U1, magnetic monopoles pick up a charge, which is theta over 2 pi times the fundamental electric charge, right? So what this tells you that, let's say you started with a U1 theory, which had no charged particles, only charge n particles. Let's work with this case. We have Zn symmetry. There were charge 0 particles, there were charge n particles, there were charge 2n particles, but there was no charge 1 particle. But you take a magnetic monopole and you do theta going to theta plus 2 pi. That magnetic monopole now has charge 1 due to the Witten effect. So starting with a magnetic charge, you could convert it into a unit electric charge using the Witten effect. So now suddenly, if you did this transformation, now your theory has a charge 1 particle, and a charge 1 Wilson line can end on that magnetic monopole particle. Okay, and so the Witten effect then tells you that in order to do the CP transformation here, we had to say pi goes to minus pi, but then we had to do a 2 pi shift of the theta angle. And that 2 pi shift of the theta angle can create charged particles where there were no charged particles before. Okay, so that is the origin of the statement that there's an anomaly. At theta equals pi, there's an anomaly between the CP symmetry. The CP symmetry involves not just taking pi to minus pi, but also shifting theta to theta plus 2 pi. So that symmetry and the one-form symmetry, which relied on absence of charged particles. Okay, this could be made much more precise. This is a little loose, but the core physics is just that the CP at theta equals pi is intricate precisely because of these branch crossings. You have to actually do a branch crossing in order to actually see the CP symmetry. Under branch crossings, there can be a physical effect where the charge spectrum of the theory could look different, and that gives us the statement that there's actually an anomaly between these two symmetries, the time reversal invariance and the Zn one-form symmetry. Okay, so this is a cartoon physical introduction to this field of higher form symmetries, and one of the nice applications of this is just this. What is the implication for this? This means that if there's an anomaly between these symmetries, if you go below the scale of confinement, if the theory was trivial, then you cannot match this anomaly. This is a theory with some anomalies, so it has to have a non-trivial vacuum structure. So the theory below the gap of the Yang-Mills theory has a non-trivial vacuum structure at theta equals pi. Otherwise, there would be no way to match this anomaly. So in which is to say that it can't be a trivial gapped vacuum. The theory below lambda QCD in this theory has to have some interesting structure, like spontaneous breaking of CP and two vacua that interchange on the CP that can reproduce this anomaly. Okay, so this is then evidence for spontaneous breaking of CP at theta equals pi in Yang-Mills theory. And it's not completely a proof, but it's very close to the only possibility in this case. We didn't use large N arguments here. This is just an anomaly matching argument using anomalies in higher form symmetry and CP in discrete symmetries. Okay. Any questions about the general cartoon picture? Don't expect you to carry all the details, but you should at least somehow have a rough cartoon of what's going on in terms of these higher form symmetries and anomalies. Yes. So sorry, say again. Um, yeah, I don't have a. I mean, it sounds plausible. I don't have a quick. I don't have a quick answer to you to say that that would definitely work. Um, Yeah, but I mean, it is it's sort of it's even in this sort of quantum mechanics example or 1+1 Maxwell theory, we can study this theory with charged particles, and we see that you actually generate a potential due to charged particles in the so certainly something like what you have in mind can be done, but yeah, I don't have a sharper thing to say than that. The usual way this is presented is using thinking about symmetry not as symmetry defect topological symmetry defect operators in Wilson and extended operators like Wilson lines, and thinking about whether the typical picture people use is, let's say you have a Wilson loop and you have a what is called a symmetry defect operator, um, and if these are linked together, and so they could have any dimensionality, but uh, the the properties that they are linked together, and so the existence of the symmetry tells you that they are always linked together. If you can break open a Wilson line, then you can unlink them, and so then you lose this property of being a topological operator. And so they usually sort of there's a but there must be a Hilbert space description of the whole thing as well. I don't know exactly precisely whether it always succeeds or there's subtleties there. Any other questions? Okay. Well, tomorrow we'll start with the massless subquark solution and the discrete solutions of the strong CP problem. Then I guess on Friday we'll do axions.